Hi everyone, welcome to my channel. My name is Johannes. In this hydraulic structure 2 course, I am going to show you some definitions and solved examples on river training development and meandering of river and the design of guide banks. So we will have some definitions, basic principles, and then we will go to examples. So I think let us start. So, as introduction to river engineering, rivers are natural channels which carry a huge quantity of water drained by the catchment as a runoff. So, if you have a catchment, then if rain is falling over the catchment, then we will get overland flow, or as a runoff we can find. So, many river systems have been seriously affected by the construction and operation of major engineering structures such as water supply project or sometimes irrigation project or hydropower project. So this river may be affected. It could be for agricultural purpose or for water supply, etc. So during construction, the overall river system will be affected. So river engineering is nothing, just the process of planned human interventions in the course, characteristics, or flow over a river with the intention of producing some defined benefit to the community, maybe for agricultural or for hydropower or flood control or sometimes for water supply. So this is just a human intervention structure. So we will just see. So the scope of river engineering, in fact, it includes river training works and also channel design works and flood control works and water supply and navigation improvement. You may have navigation and hydraulic structures design and flood hazard mitigation and environmental enhancement. So the scope of river engineering includes these topics, and we will see river morphology. So the term morphology is used to describe the shape of river channels and how they change in shape and direction over a certain period of time. So shape and direction of a river will be seen. And the morphology of a river channel is a function of a number of processes and environmental conditions, including the composition and erodibility of the bed of the banks and the sides of the bank of the river. Example, sand, clay, sometimes bedrock, we can see. So according to the morphology, just we can be viewed just by considering the longitudinal profile of a river channel, which is the slope of the channel, longitudinal slope, and the cross-sectional profile, which is the shape of the river. So longitudinal profile, just slope in different directions of a channel, and cross-sectional profile, maybe the characteristics of the banks and the natural levees, the meanders, widths, and the depths of the channel. We can see the cross-section depths and widths, and also just how it is meandering and the slope of the channel, which is side slope, and also valley flanks, braiding of the streams, and river terraces, alluvial ones, cones, and also fans, and nature of the channel floor can be treated as a cross-sectional profile. So when we say just river morphology, just the shape of the river may be changed in just in cross-section or in the direction over a time. So geomorphology, which is one other aspect, the study of landform development under process associated with running water. So geomorphology will be seen as the second part. So what will be meandering of a river? What does it mean? So if you have a bend, once a bend in a river has been developed either due to its own characteristics or sometimes due to the impressive external forces. So you may have bends of the river, then when the flow is going through the bends, then due to centrifugal action, the river is just widening or the shape will be increasing. So the process continues farthest downstream. So the excessive bends of the river's order are formed. It ultimately leads to the development of S curve, which is called meandering of a river. So when a large number of such consecutive curves of reverse order, which is S-shape, again it reverse, connected by a short ridge, which is called crossings, have been developed, then the river is called meander of a river. See the shape like this. So it will be like this. You may have deposition on this part, on the inner part, and also fastest flowing of water on this concave, which is on the outer shape of the river. Then you may have erosion and deposition. Erosion and deposition of this river cross section. So you can see here also the same. You can have just channel cliff, which is river cliff. You have due to what? Fastest water erosion on the outside of the bed, because just when it's just rotating like this, then you have erosion around here. But here, slip of the slope, then slow, shallow, and then deposition on this side will be existed. So what are the meander parameter and their relationships? Let us see now the relationships of these meander properties. Meander lengths, the tangential distance between the consecutive corresponding points of a meander, and also you have meander widths, the distance between outer edges of one clockwise loop and adjacent anti-clockwise loop of a meander. So this is meander widths and meander ratio. Also you have the ratio of meander widths to meander lengths. So you may have just connected like this. It goes on like this. This is meander characteristics of a river. So you will just see the lengths and the widths again from here up to here. Then finally we will see the property and cadres, the permanent banks of a river, which just going through these meanders or crossings, the short straight ridges of a river connecting two consecutive clockwise and anti-clockwise loop. And sinuosity is a meander, just a measure of meander intensity, how it is just going. It is the ratio between tallage lengths to the length of the valley through which the stream flows. And the tallage length is nothing, the length of the river along the line of maximum depths or center line of a river. So you may have like this, then the center line of this one may be like this. So just this is a line of maximum depth of water. So it is just we can consider tallage lengths and tortuosity, the ratio of the lengths of the channel measured along the curve to meander lengths. So this is the tortuosity formula: tallage lengths minus valley lengths divided by valley lengths. So we will have example on this one. And the stretch of a river which has sinuosity less than 1.5 determine the straight reach of a river. Otherwise, if sinuosity varies from unity for a straight reach, otherwise to a value of 3 or more than, which is curved reach. So sinuosity of 1.5 is usually taking us the dividing line, either greater than 1.5 or less than, between meandering and also straight channel. So this is a meander property, you can see. So you have meander lengths, which is complete cycle of this meandering, and the width is how it is just widening, which is from this outer edge up to this one, which is meander width. So you may have erosion at this point and deposition at this point in inner part. So these are also the relationships among meander lengths, meander widths, and river widths. It depends upon rivers in floodplain and incised rivers. So if you have a river in floodplain, you will use meander lengths according to this equation, 53.61 square root of cube. Or if you have river widths, you can use this one. Or for incised river, you have meander lengths for 6.01 square root of cube. Otherwise, if you are given width of the river, you can use 11.45. And meander widths, you can use these equations according to the given values Q, W, and meander lengths. Otherwise, for incised river, you will use this one. And river width, how do you compute? 8.84 square root of q, or q is a power of half for floodplain. Otherwise, for incised river, you use this equation. So as you note, q is just maximum discharge will be 1.5 to 2 times of dominant discharge. So dominant discharge, which determines the meandering pattern, will be given. Then you have to calculate this discharge, which is maximum. So the other topic is river training and development. So river training is nothing, a process of involving construction of structures across or along a river. So along a river or across, you will have some training structures. So most of the time, due to overflooding and weakness of material, a bank of a river may be eroded out and destruction may happen. So you have to conserve such erosion, or you have to stabilize. So stabilizing and the training of a river along a straight alignment with a suitable waterway is therefore the first and foremost aim of river training. So as much as possible, we have to stabilize the river bank and also the bed. So the most common types of river training structures are marginal embankment or levees. You can see, just to protect overtopping, we can construct guide banks or guide bends, groynes, and artificial cutoff, pitching of banks and provision of launching apron. Again, this is one training structure, and pitched island, and small check dams, gabions, riprap or revetment, and also drops, bottom seals, and bundling. So you may just provide either parallel to the stream flow or perpendicular to the stream flow, depending upon the type of structure. So we have to stabilize the banks of the river and the bed of the river. So some importance of river training works are, the first one is to guide and confine the flow to a river channel. In a fixed width, you have to guide the flow rather than outflanking to left or right of the river. You have to guide or confine the flow to a river channel, and to control and regulate the river bed configuration. This also, river bed configuration will be regulated rather than eroding out, and also ensuring safe and effective disposal of floods and sediment loss. So these are the main importance or major importance of river training works. And having this in mind, what are the main objectives of river training? The first one is to provide safe passage of flood discharge without overflowing the banks for protection of developed or inhabited areas, and to prevent the river from changing its course, and to avoid outflanking of the structures like bridges, weirs, aqueducts, etc., and to protect the banks from erosion and improve the alignment by stabilizing the river channel, and to deflect the river away from the banks which might be attacking, and also to provide minimum depths of flow and a good course for navigation. So for navigation purpose also, you will have uniform depths and also just sufficient depths of water so that navigation can be undertaken, and also to transport efficiently the suspended and dead sediment loads. So we can just transport suspended and dead loads. So let's go to the example now. Example 2.1, Meander Characteristics. So a certain river in floodplains need to be studied about the meander characteristics and its pattern with dominant discharge 2 meter cube per second and valley lengths 48 meter and tallwage lengths of 90 meter. Determine the meander lengths, the meander widths, meander ratio, and also river widths, and draw the sketch of the river, and what is the sinuosity and tortuosity of the meander. So you are given discharge, dominant discharge, and also valley lengths given, and the property which is the river is floodplain. So we will use that table, and then you have tallwage lengths. Then let us see solution. So for rivers in floodplain, you will have these equations. Meander lengths will be 6.06 times river width, and meander width will be just 2.86 times meander length, and river width, which is this one, 8.84 square root of Q, and Q is maximum discharge. Let us take 1.5 times the dominant discharge, where the QD is dominant discharge, and meander wavelength is this one. So already taken from table, because for flood planes, we are going to use these formulas. Then, so given parameter and also solution, let us see. So you have dominant discharge, valley length given, and thalweg length given. So required meander length width ratio, meander wavelength, and also river width, sinuosity, and tortuosity. So maximum discharge, let us take 1.5 times dominant discharge. It ranges from 1.5 up to 2. Let's take this one. Then you have 3 meter cube per second, and river width will be this one, 8.84 square root of Q. Then you get this one will be 15.31 meter, and meander length also 6.06 times river width. Once you have this river width, you simply plug into this W, then you get 92.786. This is the meander length, and let's go to meander width now. Meander width is 2.86 times with meander length. You simply substitute, then this is the meander width, which is 265.369, and meander ratio, the ratio of meander width divided by meander length, then it will be 2.86. This is meander ratio. Then meander wavelength will be 46 times q to the power of q to the power of this is the power of 0.39. So you have then 70.6. This is the meander wavelength. Then sinuosity will be thalweg length divided by valley length. Then you get 1.875. So you can see this is greater than 1.5. So we can see just the nature of this meander. So tortuosity, again, you have thalweg length minus valley length. If you divide by valley length, then you get 0.875. This is tortuosity. Then, since sinuosity is more than 1, which is this one, more than 1 or more than 1.5, just it is a curved ridge. Then, since meander width is very, very large, larger than meander length, the river meanders highly due to excessive hydraulic action in the bends of the river. You have this one. Then this is the sketch of the river. You have meander length up to here, up to here, and meander width is this one. So this is just erosion. Excessive hydraulic action is exerting to this bank of the river, and convex here you have sediment. So this is the thalweg length and river. Then we can go now. So please keep watching and subscribe to my channel to get more videos on similar examples. Now let's go to guide bank, design of guide banks. So the following data pertains to a bridge site of a river. Maximum flood discharge is 9,000 meter cube per second. Highest flood level is 110 meter. Lowest water level is 101 meter. And permanent bank width you have 2,000. And average diameter of silt particle given. And also top width of the guide bank will be kept at 5 meter. Side slope to horizontal 1 vertical. River bed level you have 100. And freeboard 1.5. This is just, we can assume more than 1. And the central angle of upstream curved ridge will be 135 degree. And central angle of downstream curved ridge you have 60 degree. So design and sketch the guide banks, including launching apron to treat the river or to drain the river, and find the volume of stone required for pitching the shank and the curved portion. The shank portion, which is the straight portion of the guide bank, and also the curved ridge you have. So guide bank like this, it will be like this. Then we have curved ridge upstream and downstream. So the straight portion of the guide bank is just the shank portion. And also you have, let me show you the sketch. This is the sketch of the guide bank. You can see this is just curved ridge. upstream and downstream. So river is flowing through this one, then it will go. So you have such just alignment or plan view. Now we will see the detail of this one. So find the volume of stone required for pitching the shank portion. So step one, length and radius of the guide bank. This is the first step. What is the length? So according to Lacey region parameter, so the total length or clear waterway length is given by 4.75 square root of Q. Small alluvial river. So 4.75 square root of Q will be this one. So this is the clear waterway length before which structure and allowing 20% extra length to account for thickness of piers and end contractions. So you will add 20%. So 20% or 0.2 times this clear waterway length, it will give you 90.12. Then you have cross links. Cross links between the banks will be initial length you get here 450 plus 20% of this one, you get this one. So this is the cross links between the banks. Then for Q less than 20,000 meter cube per second, upstream length of guide bank will be, you have 1.25 or 5/4 times the length, which is this one. And you can see downstream length of the guide bank will be just 1/4 times length, which is 135.18. So you can see 5/4, which is 1.25. Then you get this length, upstream length of the guide bank, downstream length of the guide bank. Then radius of upstream curved head, which is 0.45 times length. You get this length already, you have cross length. Then you get 243.33 meter. Then the upstream end of the guide bank is curved at 135 already given. So it should be between 120 and 140 degree with the radius of curvature already. You compute radius of curvature upstream head, you have 243.33. Then radius of downstream curved head will be half of radius of upstream. So already you compute radius of upstream, which is 243.33. Then half of that will be 121.665. So the downstream end of the guide bank is curved at 60 degree, already given between 40 to 60 degree with the radius of this one already calculated. Then the second step is cross section of the guide bank. Let us the given just HFL at the bridge site is 110 meter and freeboard you have, and afflux you don't have. So afflux is nothing, the rise or the heading up of water near the bridge structure. So afflux is zero, velocity is zero. Then we can have top level of guide bank, which is HFL plus freeboard plus afflux plus velocity head. Then it will be this one. So to be more safe and making an allowance for future settlement, the final level of the guide bank may be taken as just 112, just to be more safe against future settlement. So this is the top level. Then height of the guide bank above river bed level will be 112 minus river bed level. It will be 12 meter. So keep the top width of the bank already 5 meter. Then side slope will be 2 to 1 as per the requirement and site condition. So you can just draw the guide bank like this. You can draw. So you have total here HFL level. Then you have crust level, which is 12. Then if it is 2 to 1, this will be 24. Clear? So you have here 5 meter. Then you have again the same, you have 24. Since the slope is the same, then you can find. So accordingly, the stone pitching and the launching apron must be provided on the slope face of water side. Clear? Stone pitching. For the entire length of the guide bank. For the entire length of the guide bank, you have to make a stone pitching. However, the rear side of the bank must be pitched only on the curved portion. On the curved portion, we will have stone pitching on both sides. So plan view, let us see the plan view. This is the plan view. So you can see this is just on the curved portion at section BB. This is section BB. You can see this diagram. Section BB is this one. Stone pitching on both sides. Here, stone pitching is done on this side, on both sides. And for this one at section A, only on water side, which is on HFL side, you have to have this riprap placement or stone pitching. So how do you calculate now? Let's calculate. So design of stone pitching and apron. So the thickness of stone pitching on one side is given by this equation. Thickness 0.06 times maximum fluid discharge to the power of 1/3. Then you have this result 1.248 meter. So this is thickness of stone pitching. This can be kept 1 meter above HFL to protect some just collapsing or just to against wave action, we can just protect. So above 1 meter, we have to, here you have to make a stone pitching up to level 111. And silt factor, you can find silt factor is 1.75 square root of D, where D is average particle size, average diameter of particle size. So you have this one, silt factor. Then depth of scar. Depth of scar you have to calculate now. 0.47 Q over F, the whole 1/3. Then you get this is the depth of scar. Depth of scar. Then maximum scar depth is given by KRS. K times RS, where K is coefficient, which is 1.5 for straight ridge portion and 1.5 for curved portion. Otherwise, for nose portion, you have 2.25. These are coefficients. So maximum scar depth calculation and its reduced level, step 4, will be for straight reach of guide bank, you simply multiply by this coefficient 1.25 times RS, you get 12.39 meter. And depth of water above river bed level again, HFL minus river bed level. So already HFL we have 110 minus river bed level, it is 10 meter. So reduced level at maximum anticipated scar will be HFL minus scar depth, which is DS. Then depth of maximum scar already you have here. If you subtract, you get this elevation. So we will use this one for surveying purpose. And depth of maximum scar below river bed level now. Maximum scar depth below river bed level. River bed level minus reduced level of maximum scar, which is this one, 7.61. So you have 2.39 meter below the river bed level. Or you can use this one, coefficient 1.25 RS minus Y, which is the water depth. You get this one. So this is depth of maximum scar below river bed level. And length of apron will be 1.5 times D max. So already D max completed. Then this is the length of the apron. Length of the apron 3.585. This is for straight reach 1.5 D. And for curvilinear transition of the guide bank, depth of scar below HFL will be 1.5 times RS. Then you get, if you multiply by 1.5 times RS, you get 14.87. And then depth of water above river bed level, simply HFL minus river bed level, already completed previously, which is 10 meter. Then reduced level of maximum anticipated scar, which is HFL minus DS, which is maximum scar depth below HFL. You have 14.87, then 95.12. This is the elevation. Then depth of maximum scar below river bed level will be river bed level, subtract reduced level at maximum scar. So if you subtract 95.1, then you get 4.875. You can approximate up to 5 meter, or you can use this one 1.5 RS minus water depth. And then let's go to the table. So recommended scar depths at the nose of the guide bank. You have range of scar depths 2 up to 2.5. Then we are taking average of this one times RS. So this is 2.25 RS. At transition from nose to straight portion, 1.25 up to 1.75, we are taking this one. and the straight portion of the guide bank already 1 up to 1.5 RS. Then we have this one, average 1.25 RS. So we are using these values, and then how do you just see? This is just the stone pitching, which is this one. Then you have 1.5D. This is the length of the apron. So this is HFL. So water is flowing on this one. Then depth of maximum scar below river bed level will be this one, DS. Already river bed level minus elevation of this one already completed the best probable scar depths you can have. So you have HFL. So from here up to here completed, and then from river bed level up to here again we have completed. So accordingly, let us see now. Length of apron in curved portion, you have 1.5 times D max, then you get 7.5 meter. This is length of curved portion, 7.5. But for straight portion, we have completed 3.585. And thickness of launching apron for this curved portion, 1.9 times D, which is 2.37 meter. And pitching and apron on this curved portion shall be provided on both sides, which is water face front side and back side of the curved portion. So the last one is for nose portion of the guide bank at the nose. Depth of maximum scar depths below HFL will be 2.25 times RS. Then you multiply them, it will be 22.31 meter. And depth of water above river bed level will be HFL minus river bed level. Then you get the same, which is 10 meter, but reduced level at maximum anticipated scar, HFL minus depth of scar below HFL. So you have elevation, this one. Then maximum depth of maximum scar below river bed level will be D max, which is river bed level minus reduced level at maximum scar. So if you subtract from 100, you get 12.31 meter. This is at the nose portion of the guide bank, which is just like this. You have upstream and downstream curved. So nose means at this point. For curved you have, for straight portion also you have. So we will have 12.31 meter. Then the length of the apron at the nose portion will be 1.5 times D max. This is the length, the same 1.5 times D max, 80.31. And thickness of apron at the nose portion will be 1.25 times 1.248 times thickness, 1.6 meter. Then quantity of stone required. Now, slope. First, slope of scarred face is assumed to be 2 to 1. If D is the depth of scar below the bed of the river, then the length, which is the length of the scarred face, will be root 5 times D. Already you have here like this. Then this is slope you have. Then you have HFL and total you have. So this is 12 already. You have 112. This is the elevation of the crust. Then you have here 24. Clear? 24. So accordingly, you can have the side or the length of this one. Slant length. So slant length, if you multiply by the thickness, then it will be per meter length of the launching apron. So the quantity of stone required per meter length of the launching apron will be square root of 5 will be just 2 to 1, which is 1 square plus 2 square. If you multiply this one, which is radical, times D, you have D, which is the depth of scar below the bed of the river, then you will have this slant length, which is this one. Then finally, if you multiply by the thickness is 1.25 times D. You have thickness of stone pitching here. It goes on up to the maximum scar depth. Then this is just the quantity of stone per meter length of the launching apron, which is 2.80 times D. Already thickness is uniform, but D is already 2.39 per meter length. This is for the shunt portion. For all portion you can find. So the volume of stone required for pitching shunt portion of the guide bank maybe given us like this. First, you have to determine the length of the shank portion or the straight portion of the guide bank from here up to here. So upstream length of the guide bank, which is given already from here up to here, then minus radius of upstream curved bridge. You have length from here up to here, so that you can find the length of the shank portion. So 675.92 minus 243.33, you get this length. So this is length of upstream length of the shank portion. Then from section A, which is this section, which is straight portion, already I will display. For one side of the guide bank, which is just like this, only on the water face, you will have riprap placement or stone pitching like this. And again, you have here, launching apron again. Only on water side, you will just provide stone pitching this thickness. You have this length again. So volume of launching apron, first you have launching apron means here up to here. Here up to here. Then volume of slope protection, which is this length. So 2.371 already computed. Then multiplied by, this is thickness of the launching apron times the width, which is 1.5D. Then you have length from here up to here. So the overall length, you have protection like this launching apron on the bed of the river. So you have, this is volume of launching apron. Then plus this slope protection again, you have 1.248. Then square root of 12 square plus 24 square. You get this slope or this slope, clear? Side slope. Then square root of this one, then you multiply by the straight portion. So you get the volume for one side of the shank portion will be 18,163.332 meter cube. Then for the two sides, you will multiply by 2 because you have the same here, again the same. You have on both sides. We are calculating. If you multiply 36.3 to 6.65 will be the answer. So 2 times for one side. And for section BB, which is on the curved portion means you have curved portion of the guide bank at here or here. You have how many curves we have? 4 curves, upstream and downstream. So for both upstream and downstream curved portion, the pitching is done for both water side and backside of the curved portion because it may overtop and then it may take some materials. So let's see. For two sides, left and right side, you have volume of curved portion. You have 4 times volume of upstream curve. How do you get? You have such curves. Here you have protection. Here also the same. You have protection. On both sides. So 1, 2, 3, 4. 4 times upstream curved head, 4 times downstream curved head. For the curved portion, both flow is going like this. So on water face, you have to treat. On back side again, you have to treat. That's why 4 times. 4 times will be multiplied. So let's calculate now. So first, the length, the curve length or upstream curved head, you have 4 times pi r. This is the arc length of this upstream curved head, which is pi r theta, which is given theta over 180, then multiplied by, this is the thickness, and this is the length of the launching apron, then plus, this is slope protection again. You have slope again. So let me draw this. So you have riprap here. Again, you have here launching apron again. You have to treat. And on this side again, the same you have. So it will be, this is the curve length 4 times. You have 4 times for the upstream on one side like this, on the other side the same. So you have thickness multiplied by width of this one, 1.5 times d. For curved portion, we get 7.5 here. Then plus 1.248 is just for slope protection for this one. Then square root of this means just length, slant length we are calculating 12 here. This is 12 and this is 24. Then the length will be this one. So multiplied by the thickness. Then you have here again length. Then you get volume. Then plus again for downstream curved head, the same approach you will follow. But here the angle is different, which is the downstream sweep angle. Then finally 4 times upstream curved head will be this one, and 4 times downstream curved head this one. Then your result will be 141,529 meter cube of stone required for curved ridge, for curved portions. So let me show you here. This is just at section A, means just like this, like this. So for straight reach from here up to here, only on water phase or on HFL, we have computed thickness. You have slope protection plus launching apron, then times the length we multiplied. Again, for this curved portion, you have front face and back face will be treated to protect erosion, and the thickness is 1.9 times D, but here 1.5 times D max. Here again, you have the same. You have like this. So I hope this is overall volume, and you can see here is deepest scour level at this point. This is the maximum scour depth below river bed level, and at curved portion section BB you have 2.25 times D as almost this one thickness already computed, and then you have here 1.5 times D. Then on water phase you can have for curved portion and straight portion. So deepest scour portion, deepest scour level will be computed. So section BB and section A. On section A, only water phase. On water phase, treatment will be done. This is a stone pitching. Otherwise, for curved portion, both front face, this is front face, water side, but here, back side. So treatment is undertaking on both front and back side. So as exercise, we can try the following hydraulic data may describe a bridge side of a river. Flood discharge, which is 1,500 meter cube per second, highest flood level given, minimum flood level given, average diameter of silt particle 0.5 millimeter, freeboard is also given, central angle of curved portion upstream 155 and central angle of downstream curved head 55, and here afflux is given and side slope already given, and river bed level which is 200 meter, and final top level already given. Then top is so design the guide bank including launching apron to train the river at the upstream side of the weir side for extreme flood condition, and also shows the plan view and cross section of the guide bank and determines the total volume of stone required for pitching the overall structure of the guide bank, which means the volume of the shank portion plus the volume of the curved portions we will add. Then if one dump truck requires this hours per day for loading and unloading and transporting of the materials, and it works 90 meter cube per day without any problem, how many days are required to transport the materials from the quarry site to the construction site? The capacity of one dump truck is 16, and the total working hour for a single truck will be 10 hours per day. So this is exercise you can try. And the other example is linear waterway for a bridge. Determine the waterway of a bridge across a stream with a flood discharge of 225 meter cube per second. You have flood discharge and velocity is 1.5 meter per second, and with width of flow at HFL average 60 meter, and allowable velocity under the bridge is 1.8 meter per second. Then the first step is area of natural waterway will be according to continuity Q over V. Discharge divided by velocity, you get 150 meter square, and mean depth of flow area divided by length, you get 150 divided by 60. For D, we are given the width of the flow at HFL, then you get mean depth of the flow 2.5 meter, and just assuming uniform width of the channel and safe velocity 90% of allowable velocity, you get 1.62 meter per second, and area of artificial waterway will be just you have discharge divided by safe velocity, you get this one. Then, according to Moll's formula, a flux is given by the heading up of water near the bridge side, given by V square over 17.9 plus 0.015 times A square over A square, which is given area of natural waterway divided by artificial area. Then this is according to Moll's formula. Then you can find a flux heading up of water near the bridge side will be 0.024 meter or 2.4 centimeter. Then you can find linear waterway lengths. Linear waterway lengths will be A over D plus Y. Then you get this one. So this is the required linear waterway lengths. So thanks for watching. So please subscribe to my channel and also share with your friends to get more videos on similar examples.